to give, and let's hit that now. I wish more people were in here, but all right, here's one more. Almost awake even, okay? All right, let's see. Is it Jasmine Nobles? No. Okay, guessing name here. Chevette? No. What's your name? Oh man, I missed that at the very beginning. Okay. All right. Skip right past the beginning. Okay, now we have 5 people here. Only 4 here, but hopefully he's coming back. But I wanted more people here for me to make this announcement, but I'm putting it out here. Please tell your friends, okay, if they're in the class. Next Tuesday, I warned you this early in the term. Next Tuesday is my every other month visit with my hematologist. He only sees patients on Tuesday mornings. So they scheduled my appointment, I think, for 11:20. But I have to be there an hour early for labs. So I have to be there by 10:20 to get the blood work done. And that means I have to leave here right around 9:30ish. So as soon as my Math 112 class is over with, I'm heading out of here as quickly as possible. Meaning we will not meet here next Tuesday morning at 9:30. However, I do want to make the class up to you, okay? When would be a good time to do that? I don't know what time I'm getting back that Tuesday, so I don't say let's do it on Tuesday. Are Tuesdays and Thursdays better for you than Mondays, Wednesdays? Okay, I was afraid of that. The only time I've got on Tuesday, Thursday is right after this class. So if you do have it, okay. Okay. Huh? And you have a class right after this one too? Okay. Does anyone, okay. On Mondays and Wednesdays, I'm free from 3:15 or 3:30 until 5:15 or so. That work for anybody? Is anyone able to be here right after this class? That you don't have a class right after this? Anyone? I know y'all can. Anyone can? No? Okay. So it's either right after this class or Monday, Wednesday afternoon. Do you have any of those times we can do it? Well, he hasn't committed or said yay or nay. Well, that's fine. I'll record everything on Screencast-O-Matic and put it up there on YouTube. But I just would rather have someone be here to ask questions in case, or whatever. But I can do it by myself too. So you want which of those is better for you? Say again. Tuesday or Thursday, right after this class. 10:45 until, what's that? 12. Yeah, 12 o'clock. Yeah, that would do it.
I might be able to do it. It all depends on what happens.
Okay. How about Thursday of next week?
The same thing.
Yeah, you don't know yet. Okay. Let's plan. We'll meet Thursday at 9:30, and we'll find out if you can stay and do 10:45 until 12. Okay. And that's how we'll make it up. But if you can't, but think you might be able to do the next Tuesday, we'll put it off till then. Okay. Monday, Wednesday is out completely. Okay. Okay. All right, we'll shoot for next Thursday. I mean, would you want to do it today? I mean, we could conceivably do it today if you wanted to. Okay. All right. So we'll shoot for next Thursday. We will not meet Tuesday. Now, if I find out they canceled my appointment, I'll put something on Blackboard. Okay, and then I'll be here Tuesday. But the thing is, they usually don't cancel. I think we've already gotten the notification, so I think it's going to happen. All right, enough of that. Any questions or anything we've covered up till now? Okay. Where I think we left off last time, we did example 6 I think we're ready to do example 7. Okay, let me get my pen changed to dark purple because I can't change to black. Okay. And this, if there are no questions, we're on page 267, section 4.1, example 7, the bottom half of page 267. Finding angular and linear speeds. What we have here is the blades of a wind turbine are 116 feet long. That's pretty tall, okay? So here's your wind turbine. And the blades are, whoops, I may have made it too long. Something like this. Ooh, that's not it. Let me see if I can get it a little bit better looking than that. Something like that. Okay? Probably got some of those too long. Because they'd be scratching the ground, but they don't want that to happen. So the blade here is 116 feet. Okay? The propeller rotates at 15 revolutions per minute. I don't know which direction it's heading. I'll put it counterclockwise because that's what we like, but it doesn't matter whichever way it's turning. So it's rotating at 16, did I say that right? No, 15 revolutions per minute. Okay? That's the given. A. Find the angular speed of the propeller in radians per minute. So we're looking for angular speed, which we usually use the symbol omega, and they say measured in radians, which that's not really a unit, per minute. Okay, that's what we're looking for. Now, you can go through and see if you can find formulas and things like this, but frankly, let the units be your friends. They are your friends. They're trying to help you always, but sometimes we ignore them. Please pay attention to your units. Now, what looks like it might be pretty close to omega, angular speed in radians per minute? What of the entities they gave us? Which of these is more closely related to that? This is revolutions per minute. We're looking for radians per minute. Don't they even sound alike? Similar? All right, Najarian's here. He's here to help. Okay. In order to get from revolutions per minute to radians per minute, basically all we have to do is find out how many radians per revolution, right? Again, let the units be your friends. Here we start out with 15 revolutions per minute. We want to multiply this by something to give us so many radians per minute. This is just a unit thing, okay? Now, I've done these conversions with you before, right? When we were doing radians to degrees and those kinds of things, right? It's the same type of deal, okay? The first blank is for a number, and that's what we're looking for a number here. This blank is for units, okay? What are we wanting to convert from and to here? We've already got per minutes on both of them, no conversion there. We're going from revolution to radians. So those are going to be the things that go in here. One goes on top and one goes on bottom. Which goes where? Radians on top, is that what you said? Okay, and revolutions on the bottom. Okay, now let's, okay. Guess what? You can stop and think any one time you want to. Let's think about this. Okay? One revolution would be to say this went from here to there. How many radians would that cover? 2 pi. You just got your conversion. 2 pi radians covers 1 revolution, doesn't it? Right? So therefore multiply. Okay, first, revolutions cancel out. So we don't have any revolutions today. Okay, everybody's at peace. So what do we have? 30 pi radians per minute. Okay? Now if you want to actually calculate the number, pull out your calculator, multiply 30 times pi. That's going to be something around 90 some odd, maybe close to 100. Anyone got it? 30 times pi? They just left it as they left it as 30 pi radians per minute. They didn't even get it to them. Okay, around 94 radians per minute. Okay? That was pretty easy. It's just a unit conversion. You didn't even have to do much trig to it, except know that 1 revolution is 2 pi radians. So let's go to the B part. That's your omega. Omega is 30 pi radians per minute. Remember, radians really isn't a unit, but we use it like it's one. Now, the next question said, find the linear speed of the tips of the blade. So in other words, what's the velocity of that tip of the blade? Okay? Does anyone remember a formula that would help us there? If not, we could probably do it just thinking through it, but anyone remember? This is an angular speed. This is a linear speed. This is going to be in feet per minute, and that was in radians per minute. All right. Is it Chevette? No. Okay. Making me guess. Okay. Huh? Yes, I thought so. What were y'all telling me? No. Okay. Okay. We're still missing Whitney Nicole Armstead we'd never seen, but James Graves and both of our Jasmines, right? Okay. Now, anyone know how we would get from radian speed to linear speed? Remember, radians is not a unit, and we're going to need to multiply something times this to get to this. Remember, radians really aren't a unit, they're just a ratio. So we just have to multiply some feet by it. What feet do you think we need to multiply? The length of your radius. R. Yes. But V is equal to R omega. V is equal to R omega. We did that in the block at the bottom of the previous page. Omega is equal to theta over, oh, we didn't quite do it there. We did it at the last problem, I think it was. But that's what we get. And this would be 116 feet times 30 pi. Goodness gracious, this is so aggravating. And that would be radians per minute. Or actually, that is just 1 over a minute. Because radian really isn't a unit. Okay? Okay. So you just multiply 30 by 116. And I'm going to do that in my head if I can. And that would be 348 pi. And that would be feet per minute. Now, I don't know if that's the answer they give it in. No, they don't. They actually calculate that. So what do you get if you multiply 348 times 5? Say again? Oh, did I leave off a 0? Okay. 3,480 pi feet. What you get? 10,900 and what? 32. Let's leave it 33 feet per minute. Actually, that's too many digits anyway. You only have 2 digits there, 3 digits there. No way you can get 5 digits. I would say about 11,000 feet per minute or 10,900 feet per minute. You really can't get that other precision there. What did they get? They got 10,933. This is a math book, not a physics book. Okay. You see how that works? All right. If you don't, remember there is a checkpoint. Go back and try to do the checkpoint as soon as you can after class. All of you have classes right after this, except you. Okay. But whenever you can, do that, and they have the audio-video solutions at larsonplecalculus.com. All right. Any questions on that? Okay. This was example 5 that we have already done. Now, here's the next application. Sectors. Okay? It sort of starts at the top of page 268. A sector of a circle is a region bound by 2 radii and the intercepted arc. So here's a radius, there's a radius, here's the angle in between, here's the arc cut by that portion of the circle, and this gives you the sector. It's an area. When you talk about a sector, you're talking about an area. Okay? Now, what we're trying to do here is calculate the area of that sector. All right. Now, they just give us the formula. The area of a sector of a circle for a circle of radius r, the area A of the sector of a circle with central angle theta is A is equal to 1/2 r squared theta. Okay. Fine, I'll take the word for it. But guess what? What's one condition on that? To make it work, what do you have to use? Theta has to be in radians. Remember, in just about every formula you have, if you see a theta, don't put in degrees. You need to put in radians. Okay? Now, I don't know if you just like memorizing formulas or not, but let's think back just slightly. What does that almost look like, that shape? What could you almost argue that is like? What geometric shape is that closest to? Is it Jasmine Nobles? No. Goodness gracious, I'm missing everybody today. Second? You're Jasmine Nobles. Y'all are just messing with me, aren't you? Okay? And you're Chevette. Got it. All right, I marked you here. Okay. I can't hear, so that's part of the problem. Okay. We're on top of page 268. We just gave the formula for the area of a sector, but I was trying to get from you, what geometric shape does that look close to? A triangle, exactly. And what's the base of a triangle? I mean, the area of a triangle. Area of a triangle. 1/2 the base times the height. So let's imagine that. What would be the base? r, right? Now the height, that's sort of hard to figure, but let's just guess that the arc length would be that, just as an estimate. The arc length would be r theta. Remember, the theta is in radians. So 1/2 the base times the height, that's 1/2 r squared theta. That's how I remember that formula. Or, also remember the area of an entire circle. Let's go back to here. The area of the entire circle would be what? The area of the circle. Area of the circle.
Radius squared.
Pi r squared. Okay. Now, look at this. Okay. Here's your, okay. Sorry. What is the, how is pi related to that circle? It said the area was pi r squared, but the circumference is 2 pi r, right? Okay. So the pi and the r, you could think of the pi and r together, but this is a little awkward to think of it. The area of the whole circle, area of the circle is pi r squared. Okay. We're just doing a portion of the circle, right? We're just doing that portion there. Well, that portion there is theta over 2 pi, because all the way around would be 2 pi, wouldn't it? So we're just doing that fraction of the circle. Theta 2 pi's of a circle. Does that make sense? We're just doing 2 theta out of 2 pi. Okay? That portion out of 2 pi. That fraction of the circle. Okay? So then the radius is the same. So if you put, instead of, okay, we're doing theta 2 pi's, that's the fraction of the circle, times pi r squared. Okay? The pi's go away, and what are you left with? 1/2 r squared theta. That is actually how they come up with that. You're doing that fraction of a circle, 1/2 pi r squared theta. Okay? Remember, though, theta is always in radians. Okay? Now, rather than how you got it, you might just want to remember this. And guess what? Your tests are going to be open book. Go back and look it up, you know. Always look up things. Don't try to memorize, in my view. Okay. So I think we're ready to do, no, we're not. They don't have example 8 on here. Let's do example 8. Now, here's what they got. They got a golf course, okay? They got the fairway of the golf course here, and they got a sprinkler head right here. And this sprinkler head can fire out water to 70 feet, okay? And they've got it geared up to cover an angle of 120 degrees, okay? Rotates through an angle of 120 degrees. Find the area of the fairway watered by that sprinkler head. How would you get that? Say that again. Absolutely. Step number 1, 120 degrees. We're going to multiply by a conversion factor to get it in terms of radians. What unit goes where? Say it on the top. What's radians on top? Degree on bottom. What numbers match those units? Pi radians are 180 degrees. You got that right. So you can cancel out the degrees. You can cancel out a 0. We'll go into 12 and 18. 6 will go into 12. Twice. 6 will go into 18. How many? 3 times. So you got 2 pi over 3 radians. Okay? Now what? Plug it in, plug it in. The area that we're looking for is 1/2. Your radius is 70 feet squared, and your theta is 2/3 pi. Okay? I can get rid of the 2's. What's 70 squared? Second? 4,900. 0, right? Pi over 3. Okay. 3 won't go into 49 exact number of times. So pull out your calculator, see what you get. It's going to be a little bit close to 5,000, right? Huh? What do you get? Yeah. Oh, yeah. Okay, yeah. $5,131, and what unit? Square feet. Okay. Right. What's that?
What happens to that 1/2?
The 1/2? We had a 1/2 here and a 2/3 here. I divided them away. I'm just lazy that way. I don't like to multiply anything I don't have to. Okay. But you see, okay, especially when you got pi's, here's how you approximate the answer. Pi is there just a little bit more than 3, isn't it? It's just going to be a little bit more than 4,900. So I said something over 5,000. Pretty close. And in fact, I would argue you can't really say any more than 2 significant digits anyway. You may not even be able to do more than 1. So 5,000 would not be a bad guess, but 5,100 would be as good as you can, because you only have 2 significant digits there at most, and that would be at most 3. But go with the fewest. But you see that 70, you don't know if that's 70 to the nearest 10 or 70 to the nearest 1. So you don't even know how many significant digits you got there. Okay, they do have a checkpoint if you find that helpful to do. Let's look at vocabulary. 2 angles that have the same initial and terminal sides are called coterminal angles. You got it. Number 2, 1 blank is the measure of the central angle that intercepts an arc equal to the radius of the circle. What does that define? An angle measure that is equal to when the intercepted arc is equal to the radius of a circle, what angle measurement do you have? Say again? No? Okay, I'm looking for an angle measurement. We only got 2 ways to measure angles. 2 ways to measure an angle. Degrees and radians. Which is it that if the intercepted arc is equal to the radius of a circle, that defines 1 radian or degree? Radian. That's how we define a radian. The angle, the the angle when the arc is equal to the radius, that defines one ratio of that. Okay, number 3. Two positive angles that have a sum of pi halves are called, two angles add to be pi halves, complementary angles, whereas two positive angles that have a sum of pi are supplementary angles. Very good. Number 4. The angle measure that is equivalent to the rotation of 1/360th of a complete revolution about a circle's vertex is 1. The angle measure. We only have 2 angle measures. That's a degree. Very good. All right. All right. Next, number 5. The blank speed of a particle is the ratio of the arc length to the time traveled. The blank speed of a particle is the ratio of, say again, linear speed, and the blank speed of a particle is the ratio of the central angle to the time traveled. Angular speed, got it. Symbol of, what symbol do we use for angular speed? It's the lowercase omega. Okay, it looks like a little w, but it's not. Okay. Number 6, the area blank of a sector of a circle with radius r, central angle theta, when theta is measured in radians, is given by what formula? A is equal to 1/2 r squared theta. Got it. And here's the other thing to remember on that. It's right there. Okay. Is that, remember, area is measured in square linear units, like square feet, square miles, square centimeters, whatever. You have to have r squared. Have to. Theta is a ratio. It's not got an angle, unit. So that's where you get it. So remember the r squared. R has to be squared. Okay. Homework exercises. I gave some of these before. Here are the others. Either 7 or 9. Do number 11. It has 2 parts. Do number 13, it has 2 parts. Do number 15, it has 2 parts. Do either 17 or 19, or both if you choose. Either 21 or 23, or both. Do 25, it has 2 parts. Do 27, it has 2 parts. Do 29, it has 2 parts. And do either 31 or 33, or both if you choose. Do 35, it has 2 parts. Do 37, it has 2 parts. Do either 39 or 41, your choice, or both. Either 43 or 45, or both. Now, did anyone try 47 at home? Uh-oh. No one tried it. Okay? We hadn't done any like it in class. That's why I suggested you try that. I can do 48, so you can still do 47 at home. You want me to? Huh? Yay? Okay. Let's do 48. I was hoping y'all would do it. Tell me if you had any trouble with it. Not? Okay. Okay. This is page 270. 4.1 exercise, I think it's called. Yeah. And this is number 48. So we can't check in the back of the book, see if we got it right. Just going to have to trust me, folks. I've got some swampland in Florida. I'll show you. Okay? All right. Give it to you. Okay, no problem. 48. Negative 135 degrees, 36 minutes. Negative 135 degrees, 36 minutes. Okay? What we're asked to do is convert that angle measure to decimal degree form, and it says without using a calculator. And then check your answer with a calculator. So how do you reckon we're going to do this? And again, they didn't go over this in class. It's going to require you to know a little bit of something. Well, we want it in degrees, so let's leave the negative 135 just like it is, but I need to get 36 minutes into degrees. And there's something you need to know for that. How many minutes in a degree? 60. Remember, we're doing the good old Sumerian method. They had some sort of base 60 system. So that would be 36 minutes out of 60 minutes in a degree, right? That fraction. Okay? Can we simplify that any? Second? Divide by 6 and you get 6. Divide that by 6 and you get 10. I wouldn't go any further. Make this negative 135.6 degrees. Because 6 over 10 is 0.6, right? Okay. That's not using a calculator, then you can use a calculator if you want to. Let's look at the B one. Okay. Negative 408, negative 408 degrees, 16 minutes and 20 seconds. Oh, wait a minute. I wrote, oh, yuck. I misread that. I wrote seconds, but then treated it as it was degrees. That's wrong. Okay, sorry about this, folks. That was 36 seconds, not 36 minutes. I just wasn't paying close attention. I wrote seconds, but I wasn't paying close attention. How many seconds in a degree? Say again? There's 60 minutes in a degree. How many seconds in a minute? Same thing with time. 60. So you got 60 times 60, which is 3600. So that's what should be on the denominator here. This is 36 seconds out of 3,600 seconds. And that would be what? 36s go out, and that leaves you negative 135 100th. How do I write that as a decimal? 0.01 degrees. That's your answer there. Sorry. I was doing minutes and it was seconds. Okay, so the second one here is negative 408 degrees, 16 minutes, 20 seconds. Okay. Now, I kind of like to do this in two pieces. You might want to do it in one, but I find it a little easier to see this way. Okay, that would be negative 408 degrees because we're trying to get to degrees. Okay. And let's leave the 16 minutes alone for now, but let's write the 20 seconds as a fraction or as a decimal of minutes. 20 seconds is what portion of a minute? 20 over 60. 20 over 60 minutes. Okay, so actually, there's no reason to put the units twice. Whoops. It won't take. Okay, that time it did. And 20/60th of a minute. Okay. Now, I think for funsies, let's just simplify that. The zeros go out, and that would be 2 over 6 is 1 over 3. So that would be negative 408 degrees, 16 1/3 minutes. Right? Okay. This one's messy, especially not to use a calculator. Minus 408. And then I'm going to do that 16 1/3. By the way, it's 49/3, right? Got it? Agree? So I'm going to write that as 49 9/3 of a minute, but write that over 60, right? Because you're dividing by 60. So that would be 49 over 180. Frankly, that is a messy number. But we'll leave it like that. So that would be negative 408 and 49 1/80ths of a degree. Okay. Now, let's write that as a decimal number and see what you get. Yeah. Okay. That one's just inexcusably messy, especially to say do it without a calculator. Okay. Now, did any of you do number 49? I thought not. So let's do 50 to see if you can, we can get that one. So what I'm going to do, I think I'll erase it all and just, we're going to use the same thing, same page, same thing. It's just number 50. Okay? We're going the other way now. 50A says, what if you start with negative 345.12 degrees. And what you want to write that as in degree, minute, seconds. Okay? Yeah, degree, minute, second form. Now we go the other way, right? And this is actually the easier to do. This would be negative 345 degrees, and 12/100ths of a degree would be exactly that. How many minutes in a degree? 60. So do your 60 and multiply by 0.12. Okay, that would be 7.2 minutes. Because what you're multiplying by, this is degrees times minutes per degree. The degrees go out and you're left with minutes. But we don't want a decimal in there, so we take that 2/10 of a minute, 0.2 minutes, multiply that by, we're trying to get the seconds now. And what unit would we put where? Unit would we put where? Trying to get from minutes to seconds. Minutes on the bottom, seconds on top. I'm just doing this a different way. How many seconds in a minute or minutes in a second? 60 seconds in 1 minute. And you multiply 0.2 by, that's the same way we did before. And 0.2 times 60 would be 12, right? 12 seconds. So that would be negative 345 degrees, 7 minutes. I put seconds there. Goodness gracious, I can't believe I'm doing that. Okay. 7 minutes, 12 seconds. Yuck! Okay, 12 seconds. You just take the 7/10 of a degree, 12/10 of a degree, multiply it by 60, and that will give you 7.2 minutes. And then multiply the 0.2 times 60, yeah, and that gives you 12 seconds. Okay. Want to do the B? The before was pretty messy. Let's see how this one is. Negative 3.58 degrees. Okay. You tell me. Would that be negative 3 degrees? How do you get 0.58 degree into minutes? Multiply by 60. So 0.58 times 60, 48. That would be 34.8 minutes. Okay, how do you get the 0.8 to seconds? Multiply by 60. So 0.8 times 60. I think that comes out that's 48 seconds. So this will be negative 3 degrees, 34 minutes, 48 seconds. Okay? Because this only has one decimal place. See what happens. Okay. 48 seconds. See how that works? One way you're dividing by 60s, other way you're multiplying by 60s. Okay? It's a unit conversion. That's all it is. All right, that was, you do 47, there are 2 parts, and 49, there's 2 parts. Do 51, there's only 1 part there, but just do that. Do 53, only 1 part there. Do 55. And then do 57, okay? Then you choose which word problems or applications you want to do. Any of the odds, 59 through 69. Okay? Now, under the exploration, true, false, you'll not see any of these on the test, but it's still a good thing to think through, as are 75 and 77. Those are just think-throughs. And then we move on to 4.2. Any questions before we move on to 4.2? Okay. All right. All right, let's move on to 4.2. Now, I can't remember if all of you were here that first day when we talked about what we're going to cover. We do the first 4 sections here. I'll give you your first test. Next 4 sections, the second test. Then Chapter 5, the third test. Chapter 6, the fourth test. Okay. This is slow, but it's happening. Yuck! This is so slow. So here, if you think about it, we just covered a whole section there. How many trig functions did we deal with? Not a one. We talked about angles, we talked about sectors, we talked about areas, we talked about conversions, but we didn't do really anything with trigonometry. This is where the trig really begins. Well, I thought it would. It took all that time and didn't open. PowerPoint is just really screwy. I do not like Microsoft products at all. They're ubiquitous. You have to use them, but man, they're a pain in the... There we go. Okay. All right, trigonometry. What does that word mean? Measurement of triangles. But we're not going to do triangles yet. We're going to start with circles. When I first remember doing trig, we started with triangles. We got the ratios of that. Then we did the unit circle and saw how it related. I still think in those terms, but the books always present unit circles first. So let's do it. Trigonometric functions, we're going to start with the unit circle. We'll identify what in the world do we mean by a unit circle. What would you say we mean by a unit circle? Circle what? Any of you ever played that game that you put down colors or cards and stuff, and then when you have one left, you say, uno. What does that mean? One left. So what do we mean by uno? I mean unit circle. Yeah, a radius of one. One card, one radius of one. That's what a unit circle is. I just identified. Describe its relationship to real numbers. That sounds like a weird thing. We'll do that. Evaluate trigonometric functions using the trig unit circle. We're going to find that's a pretty easy thing to do once you get it down. And we'll use domain and period to evaluate sine and cosine functions, and use a calculator to evaluate trigonometric functions. So let's start with uno, or unit circle. Circle, radius 1. The two historical perspectives of trigonometry incorporate different methods for introducing the trig functions. Frankly, they started with triangles, measurement of triangles, and yet we start with the circle. Once those perspectives follows, it is based on the unit circle. This is the one that came along later, I think. So here's what a unit circle is. It's a circle whose radius is 1. Now, what is the general equation for a circle? If I said, write an equation for a circle in x's and y's. Any old circle. It would be, there's actually a couple ways to express it. I'll show you both of them. The simplest, if it's centered at the origin, it's x squared plus y squared is equal to r squared. That's what a circle is. X squared plus y squared is equal to r squared. Okay? Actually, you could say it this way. X over r squared plus y over r squared is equal to 1. That's another way to express it. You just divide both sides by r squared and then write those separately. That's a circle. Okay? Now, if that radius is 1, then this is true. In a unit circle, it's always 1. This is centered at the origin. Now, if it was centered somewhere else, let's say a point AB, A for x and B for y, then this would be x minus a squared plus y minus b squared is equal to r squared. We're not going to do that. We're going to leave it at the origin, so you don't have to worry about that. So this is true about every point on a unit circle. X squared plus y squared is equal to 1. If you take this point right here, its x value squared plus its y value squared is equal to 1. It calls a Pythagorean theorem, right? A squared plus b squared is equal to r squared. And if r is 1, or c squared, if that c is 1, then it's equal to 1. That's going to be true for every point on the circle. Believe me? Okay. Unit circle, radius of 1, that means a diameter 2, but radius of 1. So this point is 1, 0, 0, 1, minus 1, 0, 0, negative 1. That's if it's centered at the origin. That's true of every unit circle. Period. Okay. Now, this part, I understand what they're doing. Imagine wrapping the real number line, which is a line, bending it so it wraps around that circle, unit circle, with positive numbers corresponding to counterclockwise. So positive is going up here. We're going to take that and wrap it around that unit circle. Okay? Negative numbers would be if you wrapped it clockwise. Counterclockwise, positive, negative would be clockwise. Okay? Now, sort of a weird concept, but that's what you do. Number line, you bend and wrap around the circle. Okay. What if you know that distance right there is 1, right? Unit circle, radius is 1. What if this distance was also 1 exactly? Then this would be a measure of ratio of arc length to radius is your radian measure. That would be 1 radian. But if it's something other than r, then t over 1 would be this ratio. This t divided by radius 1 would be t. So this is relating that arc length to any real number t. That would be how far around there you're wrapping on the unit circle. Or this way, negative t. Okay? As the real number line wraps around the unit circle, each real number t corresponds to exactly 1 point xy on the unit circle. So this value t right here, that's 4, whatever those units are up here, okay? That wrapped around that corresponds to this xy point. This number, positive t, represents that. This negative t number down here represents this xy point, okay? So, for example, the real number 0 corresponds 0 here or 0 here. You're at the point 1, 0, right? Okay. Moreover, because the unit circle, what is the circumference of that unit circle? What's the circumference of any circle? 2 pi r, and if your r is 1, unit circle, r is 1, uno, then you've got 2 pi. So you're absolutely right. Moreover, because the unit circle has a circumference of 2 pi, the real number 2 pi also corresponds to the point 1, 0, because you made 1 complete circle. So that was 0, and it's also 2 pi. Well, that's your basically coterminal angles we were talking about before. Okay? In general, each real number t corresponds to some central angle in standard position whose radian measure is t, because the ratio of the arc length t to the radius 1 is t over 1, which is t. So that not only is that the arc length of a unit circle, it is also the radian measure of that unit circle. With this interpretation of t, the arc length formula, S is equal to RT. We had that before in the first section. But if R is 1, S is equal to theta. S is equal to theta if R is equal to 1. Now, I sort of don't like for them to say that. In fact, they didn't say it. I said it. Because S is measured in a length measure. That's the arc length. Theta is measured in radians. That's just a ratio. Your unit for this comes from the R. But because R is 1, we ignore the unit. So whatever the unit for R is, that's the unit here. But the magnitude of S is just theta because R is 1. Okay. So this indicates that the real number t is the directional length of the arc intercepted by the angle theta measured in radians. So the real number t, in other words, that value of S is the same numerical value as the angle theta in radians. A lot of blah, 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 wasn't it? Okay. So let's move on to the trig functions. We finally get to the trig functions. From the preceding discussion, it follows that the coordinates x and y are two functions of that real variable t. Remember? The real number, real variable t. Whatever it was, it identifies an x and a y. Okay? You can use those coordinates to define the 6 trigonometric functions. Now, this time, they're spelling them out for you, and I hate that they put them in this order, because I don't think of them in this order. It makes sense, but only if you know what they mean. I think of them this way: sine, cosine, tangent, cotangent, secant, cosecant. Now, we usually don't write them out. We usually write first 3 letters here, sine, first 3 letters here, cosine, first 3 letters there, tangent, first 3 letters there, cotangent, first 3 letters there, secant. Do we do the first 3 letters here? No, because that would be cosine, okay? So you have to do something on this one. Take the first 3 consonants, CSC. That's the symbol for cosecant, okay? So these 6 functions are normally abbreviated SIN, don't say sin, sine, cosine, tangent, cotangent, secant, cosecant, okay? CSC, that's the one with only consonants, okay? So far, we just named them. We haven't told you what they are. These are their names. Okay? Let's see what they are. Here's the definition of those things. Now, again, remember, we're on the unit circle. What's the radius of a unit circle? 1. Okay. But on the unit circle, if t is a real number corresponding to an angle, then let xy be the point on the unit circle corresponding to that angle t, angle in radians. Remember, it's always in radians. Okay? Sine of t is the y value. That's it, folks. On the unit circle. The cosine of t is the x value on the unit circle. The tangent of t, you can think of it several ways. It's the ratio of y to x, which also, by the way, is the ratio of sine to cosine. Okay? We're not going there yet, but note that. The ratio of y to x. Now, here we run into problems, right? Because x can be 0 on the unit circle. X is 0 on the y-axis, right? So down here and up here is 0. So the tangent is not defined at the angle up or the angle down, vertically up or down. Not defined because you can't divide those here. Now, I like to go this way. Cotangent, then, is the reciprocal of tangent. It's the ratio of x to y. But now we can't allow y to be 0 because that's in your denominator now. Because cotangent is not defined at 0 and pi. Oops, yeah. Okay. Now, secant, and the reason they wrote it under here, is the reciprocal of cosine. 1 over x. But now again, x can't be 0. And cosecant is the reciprocal of sine, which is 1 over y. Okay. Now, this is for future reference. Okay? What was the radius of that circle? 1. Okay? And notice we have a 1 here and here, which means we could have written y over 1 or x over 1, right? So I like to say it this way, just because it will help me later. This is fine for the unit circle, but guess what? If you have any old circle, all you have to do is y over r, x over r, x over y is x over y, y over x. y over x, x over y, they're fine. This would be r over x and r over y. You still have the same ratios. Okay? On the unit circle, it's just that the r is 1. Okay? So we'll come back to that later. Unit circle, all you have to remember is that. Okay? In those definitions of trigonometric functions, notice that the tangent and secant not defined when x is 0, and the cotangent and cosecant are not defined when y is 0. Okay? For instance, at t equal pi halves, where is that? You should remember that. T is equal to pi halves. 90 degrees, exactly. A quarter of a circle. Okay? At t is equal to pi halves, when you're up there, you're at the point 0, 1. Where your x is 0 there. The tangent is not defined at pi halves, or 90 degrees. Tangent is not defined there. Okay? Neither is secant. Similarly, the cotangent and cosecant are not defined when x is 0. That's it. Either theta equals 0 or theta equals pi. Both places your x is not. So if t is equal to 0, you do not have a cotangent or a cosecant. They're undefined. We'll see this later. Okay? Now, this figure 417, and in the book that's the middle of page 273, the unit circle is divided into 8 equal arcs. Okay? According to these t-values. If you got a whole unit circle, how far is that around the unit circle? Say again? I can't hear it. How far is it around the unit circle? Okay. Okay. Or in radians? 2 pi. Think radians, folks. Okay. 2 pi. Now, if you divide that 2 pi by 8, this would be 2 pi divided by 8, which would be pi divided by 4. So you're at pi fourths. 2 pi eighths would be, 4 pi eighths, this is 2 pi divided by 8, 2 pi divided by 4 would be pi halves. 2 pi divided by 3 pi is what I'm trying to say. 3 of those sections, okay, divided by 8. 2 pi divided by 8 and use 3 of them. Okay. 2 pi divided by 8 would be pi fourths. 3 of those would be 3/4 pi. That's this one. Okay. And 2 pi divided by 8, 4 of those would be pi. Okay. 5/4 pi, 6/4 pi, which is 3/2 pi, 7/4 pi, 2 pi. You've divided it by equally by 8s. Okay. Those are your angle measurements in radians, but what xy values? We know these, 1, 0, 0, 1, minus 1, 0, 0, minus 1. But what's the point right there? Okay? How do we get that? They wrote them in, but how do we know that's true? Okay, here's how. Notice this line exactly bisects this quadrant, right? Exactly. So guess what line that is? Huh? It's on a tangent. That's what you said. I can't hear well. What line is this? If you had to write that as an equation for me, in x's and y, what line is this? At exactly halfway between that. If you go over here at x, guess how far you can go up here? What's the relationship in the x and y? They're the same. That's the line y is equal to x, isn't it? Because that's the diagonal there. Y is equal to x. Okay? Now remember, if it's a unit circle, what's always true about a unit circle? X squared plus y squared equal 1. It's a unit circle radius of 1. You just told me here that this line was y is equal to x. So you choose which one you want to substitute in. Y is equal to x or x equal y, I don't care. What would this become then? You want to keep the x? Okay, so that'd be x squared plus, and what's y equal to? What's y equal to? X. On that line there it is, isn't it? So this will be x squared again, wouldn't it? So x squared plus x squared is equal to 1 on the unit circle on that diagonal line, right? What would this become? What's x squared plus x squared? 2x squared is equal to 1. Now what might we do? Divide both sides by 2. That gives you x squared is equal to 1/2, right? So x is equal to what? Square root of 1/2. Only when you're taking the square root of both sides of an equation, you have to do a plus minus, don't you? Well, what's the square root of 1? 1. What's the square root of 2? Square root of 2. Okay? Now, if we don't like radicals in the denominator, what can we do? Multiply numerator and denominator by the square root of 2. Right? So this will be plus or minus the square root of 2 over 2. And what did they get? X is equal plus square root of 2 here minus square root of 2 down there. Right? And if x is equal to y, your y is square root of 2 and negative square root of 2 down here. Right? Hey, okay? So guess what? We just found these 2 points. This point right here, root 2 over 2, root 2 over 2. You could have written it 1 over root 2 if you don't mind having radicals in the denominator, 1 over root 2. Or this way. Down here, same thing, only opposite. Over here, the anti-diagonal, that would be true except x is equal to minus y, or y is equal to minus x, and then they swap sides. Okay, we didn't get much further there, but we got a little bit, and we are ready to do the second figure there. Okay, y'all are really anxious to leave, aren't you? Okay. All right, let's see. Did we do enough for any homework exercises in that section? Maybe not. You can just do the ones in the previous. We'll pick up from there and go from there. Good deal.